we're going to talk about the characteristic equation. And basically what this does is this is our method or means method to find the eigenvalues. So pretty crunchy. So let's see how this works. To find eigenvalues of a square matrix, we are finding non-trivial solutions to the equation A minus lambda I times X equals 0. By the invertible matrix theorem, this is the same as finding lambda such that A minus lambda I is singular or not invertible. But this occurs when, remember, we had that long theorem of ways that a matrix could be invertible or could be not invertible. And I had you add one to the list. What's the one that I had you add to the list? So it's invertible when the determinant is not 0. So it's singular or not invertible if the determinant is 0. Kind of using it in the flip-flop side. So we want to find the eigenvalues here of A equal to 5335. And so what I need to do is I need to work with A minus lambda I. This very first time I will write it out. So this would be like 5, 3, 3, 5 minus I times lambda, which would be lambda 0, 0, lambda. Or in other words, 5 minus lambda, 3, 3, 5 minus lambda. So you'll notice that you end up with your diagonal entries minus lambda showing up. And so what we need to do is we need to solve for when the determinant of this thing is equal to 0. So to find the determinant of a 2x2 matrix, you're going to do your AD minus BC. So we will have 5 minus lambda times 5 minus lambda minus 9 equals 0. Okay. How does this factor? Minus 8 and minus 2. So this tells us that lambda is equal to 8 or lambda is equal to 2. Notice that our matrix A that we started with was a 2x2 matrix. We just found two distinct eigenvalues. So there must be 2 linearly independent eigenvectors that we could find if we were so inclined. So 2. So this allows us to add to that invertible matrix theorem. And so we saw before that the matrix is invertible if the determinant is not 0. And now we're adding to that that the number 0 is not an eigenvalue. Evan asked, how do we assume it's not invertible? Let me go back. So remember, if you think about the eigenvalues and eigenvectors, they're only going to take place You're only going to have an eigenvector if you have a non-trivial solution to the equation a minus lambda I times x equals 0. So non-trivial solution to the homogeneous equation means that this matrix a minus lambda I must not be invertible. That makes sense, Evan? Cool. Hey. Other questions before we go on? So some properties of determinants, and I think we've seen all these before. So we have the A is invertible if and only if the determinant is non-zero. We already saw that the determinant of a product is the product of the two determinants, and that's going to come in handy later on in this section. And then the determinant isn't impacted by the transpose. This last one should make sense because remember, it doesn't matter whether you expand across a row or across a column, you're going to get the same determinant. Pardon me. In D, if A is triangular, then the determinant of A is the product of the entries on the main diagonal. This is really handy. So pro tip, if you're ever in a test situation and you're given a triangular matrix, that's your teacher trying to say, here's the eigenvalues, here's the determinant. Like they're just sort of like trying to hand you a whole bunch of stuff. And then this E part is just a reminder of how the determinant is impacted by the row operations. Another pro tip. Don't use this to find eigenvalues. It works mathematically, like the math works, but it's a pain. And very, very few students, in my experience, are able to follow along like by hand in doing that. So don't take that route. If you don't believe me, try it on a 2x2 and see what happens. And just see how it plays out. Okay, onwards and upwards. So we can now determine when the matrix A minus lambda I is not invertible by solving this equation. So notice we have this equation to determinant of A minus lambda I equals 0. That determinant comes up a lot, and so it's called the characteristic equation. If you look at the top of your page, I think you'll see that the name of this section is eigenvalues and the characteristic equation, right? So this thing's a big deal. So let's find a characteristic equation. So here we are in example 2. So if I want to find the characteristic equation and the eigenvalues of A, then that means that I need to solve 0 equals, and then I'm no longer going to write the det. I'm just going to use the vertical bars for the determinant. So I have 4, 0, 0, 5, 3, 2, minus 2, 0, 2. And then in order to make this work, I have a minus lambda, minus lambda, minus lambda along the diagonal. Any particular rows or columns that you would recommend we expand across? Yeah, first row all the way. So we have 4 minus lambda times 3 minus lambda 2, 0, 2 minus lambda, which in this case, it works out to be pretty nice. 4 minus lambda, 3 minus lambda, 2 minus lambda, which tells us that lambda equals 2, 3, 4. Yeah, middle column would have worked just as well. Good call on that one, Tommy.
Dusty, does it matter which order you put in the lambdas? Like,
no, I would suggest either increasing or decreasing. I think actually it can be helpful to think about them as put them in the almost the opposite order of, come on, of the 4, 3, 2. And we'll see. I'll get to your question in a second, Ahmed. We'll see why later, but basically the eigenvector associated with the 4 is the most important information in the transformation. And then the next most important information is the stuff associated with the 3, et cetera, et cetera. So by going from biggest to smallest, we kind of are organizing from teaching ourselves to organize from most important to least important. But there isn't a have to at this stage. Good question. Ahmed asked the question, why isn't it 1/3 minus 2 minus lambda? I think, Ahmed, what you're looking for is, in your question, is the inverse. So remember, if you're finding the inverse of a matrix, if you have A, B, C, D, this is your A, then A inverse is equal to 1 over the determinant of A times the dA minus B minus C. And what we care about here is actually the determinant itself, not the inverse. Does that make sense? Cool. All right. Let me just say one more thing and then we'll call it a day. So maybe it's 2 more things here. So if I put an equals 0 here, what's the name of this equation? So this right here is the characteristic equation. Yeah, characteristic equation. And it's the characteristic equation. What I want to comment on is that this part right here, I'm using yellow for too many things. No. That the blue part, not the equals 0, which would be just this coming from the right side, this is what's called the characteristic polynomial. Okay. So you have the characteristic polynomial is the part that is the polynomial, and then if you said it's equal to 0, then we would call it the characteristic equation. So it's two similar things. I'm just mentioning it here because we're going to start with this tomorrow, and I figure it's like low-hanging fruit. We'll make the tomorrow a little bit of an easier day. So we're going to continue talking about eigenvalues, eigenvectors, and then this is going to lead directly into the idea of diagonalizing a matrix, which in turn ties into the reading assignment that some of you have probably already completed and others of you are probably working on. So there's like today connects directly with the reading a little bit. So in example 3, I'm going to begin by finding the characteristic equation of A equal to this matrix. Can you tell me any special features of this matrix? See something special about it? It's a triangular matrix. That's exactly right. Thank you. Thank you, Felix and Ben. So it's a triangular matrix. You'll notice that you've got these zeros up there. So if we want to find the characteristic equation, this would be 0 equals the determinant of A minus lambda I, or 0 equals the determinant of, what do we have, 4 minus lambda, 2, 3 minus lambda, 3 minus lambda, -1 minus lambda. Something like that. And if you want to find the determinant of a triangular matrix, what do? I think we've talked about this before. So from Dibs and Felix and Kevin, we're going to take all these diagonal entries and multiply them together. And so we're going to get 0 equals 4 minus lambda times 3 minus lambda squared times -1 minus lambda. So this is right here. This thing right here is our characteristic equation. Okay. So this tells us that our eigenvalues are lambda equals 4, lambda equals 3, and lambda equals, what do we have, -1. So I want to point something out here, that you have the 3 eigenvalues, and there's something kind of special happening around lambda equals 3. What's special in the characteristic equation around lambda equals 3? So from Gerald, it's happening 2 times. From Felix, you've got a multiplicity of 2. And so, yeah, I want to point out that you have that power of 2. And so we would say that our algebraic multiplicity is 2. And again, that 2, whoa, orange, that did not work. Sorry, let me change my colors. That didn't work either. Sometimes something's a great idea that just doesn't work. And we don't really have a good sense for what that means or what that can do yet, so just kind of hang tight. At this point, I'm just pointing it out. In this case, from Dibs, yeah, actually it's pretty cool that the eigenvalues here, 4, 3, and 1, and -1, those are just the diagonal entries. And so we could have saved ourselves a whole bunch of work by just pulling off those entries. So that's totally legit. So good call. But I wanted to make sure I'm highlighting what's the characteristic equation as well. Okay, so let's see if we can summarize that. So if A is an n by n matrix, then the determinant of A minus lambda I is a polynomial of degree n called the characteristic polynomial. We talked about this at the end of class yesterday, but just in case you don't remember that, the green thing up here is the characteristic equation, but the part that's just here in black would be our characteristic polynomial. So everything except for the equals 0 part. So the eigenvalue of 3 in the previous example is said to have algebraic multiplicity 2, just like we talked about. Algebraic multiplicity 2, because the factor of x minus 3 I don't know what you're
calculator.
The factor of lambda minus 3, actually 3 minus lambda, occurs twice. And that twice is again this same 2 that we've got up above in the characteristic polynomial. So suppose that we had a 7 by 7 matrix. So since it's a, remember that if you have an n by n matrix here, then you're going to have a polynomial with degree n. So if here we have a 7 by 7 matrix, we're going to end up with a polynomial with degree 7. So here's that 7th degree polynomial, characteristic polynomial. We want to find the eigenvalues and their multiplicities. So just factor so common factor of lambda cubed, and then I'm left with lambda to the 4th minus 8 lambda squared plus 16. And so it's a little bit, maybe it's a little bit hard to see, but lambda to the 4th minus 8 lambda squared plus 16. This is a quadratic in disguise. So this is like a squared minus 8a plus 16. So you could factor that to be a minus 4 times a minus 4. So we have lambda squared minus 4, lambda squared minus 4. So I lost the lambda cubed. Or in other words, we have lambda cubed times lambda plus 2 squared, lambda minus 2 squared. So our eigenvalues and their multiplicity. So it looks like from here we have lambda equals 0 with multiplicity what? It's lots of 3s. Thanks everybody. And from here we have lambda equals -2 with multiplicity 2. Tons of 2s. Thanks everybody. And last but not least, we have lambda equals 2 with multiplicity 2. And you'll notice that even though there are only 3 distinct eigenvalues, 3 different eigenvalues, if you add up the 3 numbers together, I guess 3 and 2 and 2, you add all those together, I think that adds up to 7, which matches the 7 by what we said before about that 7 by 7 matrix. All right, so I'm going to introduce a new concept called similarity. So we would say that 2 n by n matrices, these have to be square matrices, are considered to be similar if there is an invertible matrix P such that P inverse AP equals B, or maybe you want to write A equals PB P inverse. Okay. Before we get too carried away, let me just make sure you have some idea why this matters. So what's this whole thing about similar about? This is the same transformation, but with respect to a different basis. Same linear transformation, but with respect to a different basis. Okay. So that's what this whole section is about. Notice in my equation here, right, I could start with the P inverse on the left of the A, or you might say, well, that's not cool. Like, how do I remember which is which? Well, good news, it doesn't really matter. If you don't like, you're like, what if you forget about where the inverse goes? Same thing holds. So we could have had like Q A. Whoa, that's the wrong one. Wrong pen, sorry. Q inverse equals B. So notice what I did is here's the inverse. Here it's on the front end. Here it's on the back end. Kind of like what, or you could do it the other way. What's the relationship between P and Q here? Oh, thank you. There's a couple people in the waiting room. Appreciate the note there. Yeah. So in this case, we're saying that P equals Q inverse. They're just sort of inverses of each other. Thank you, Evan. Okay. Welcome in. I had a couple of you guys just come in from the waiting room. Hope I didn't leave you there too long. I'm sorry about that. Okay. I've got from Gerald, what is WRT? Anybody remember this or catch that? Yeah, from Megumi, with respect to. Very good. All right. So if we want to change that matrix A, and we want to do a transformation to like almost to itself, so we don't want to change anything. So changing A into P inverse AP is called the similarity transformation. Okay, so again, we haven't really done anything with it. We've just introduced this new idea. So we're saying we got these two matrices A and B. They're similar, and I haven't done any sort of proof, but I'm just telling you that's basically the same transformation, just with respect to a different basis. This next theorem connects the similar matrices back to the characteristic polynomial that we were just talking about. Because you might have been thinking, wait a second, I thought we were talking about eigenvectors and eigenvalues. How do these connect? So theorem 4, if an n by n matrices A and B are similar, then they have the same characteristic polynomial, and and hence the same eigenvalues with the same multiplicities. So this is actually a nice, relatively straightforward proof. So here's our claim. So we have n by n matrices A and B are similar. So we got to start by defining the things we're talking about. Let n by n similar matrices A and B be given. So let's see, what does it mean for them to be similar? Look up at the definition. So anytime you see similar, you got to continue on similar. That means there is a matrix P. There is this invertible matrix P. So that's where we're going to go next. So we've got n by n matrices, similar matrices A and B given. This implies that there exists an invertible P such that, and we could write this a lot of different ways. Maybe I'll write it this way, that B equals P inverse A P. Okay. Thanks to others on the answering the question about the WRT. All right. So the question then talks about they have the same characteristic polynomial. We don't have a characteristic polynomial, so let's see if we can bring that characteristic polynomial out. So the characteristic polynomial of B would be B minus lambda I. So this is the characteristic polynomial of B. We're trying to show that it's the same as the characteristic polynomial of A. Okay. Well, this would be equal to, we could take that B, and you'll notice that the B here is the same as the B there. So we could replace, so this would be the same as P inverse A P minus lambda. Can you think of a nice fancy way of writing the I that's here? From dibs, don't we have to have a determinant in there too? Yes, thank you. We are going to have a determinant. You're correct. This is not the characteristic polynomial. This is the determinant of this will be the characteristic polynomial. You're correct. But this is our intermediate step. So thank you for that. And Ahmed, perfect. We could rewrite I as P inverse times P. So this allows us to write, to pull all the P inverses out front. And so then I've got A minus, boom, there's another I that just shows up, and then a P inverse, sorry, a P at the end. So like Dibs reminded me of, in order to have the characteristic polynomial, we need determinants. So this tells us that the determinant of B minus lambda I is equal to the determinant of P inverse times A minus lambda I times P. And I'm hoping you remember what we can do with the determinant of a product. So if you have the determinant of a product, you can write this as the product of the determinants. So the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. What can you tell me about the determinant of P inverse and the determinant of P? They're probably not equal to each other. Inverses is a funny word. They're reciprocals of each other. So determinant of P equals 1 over the determinant of P inverse. Yeah. So if I have a determinant of P inverse times a determinant of P, what's that product going to be equal to? From James and Ryan and Ben and Alex and Adis, Cortana and Twee, it's going to be a nice, happy 1 times the determinant of A minus lambda I. So notice that what we just said is we just said that the determinant of B minus lambda I equals the determinant of A minus lambda I. That is, their characteristic polynomials are the same and their eigenvalues are the same. I got a question from Kyle. Is the reciprocal still to the negative first power? Yeah. Yeah. So like 2 to the negative first power would be 1 over 2. If you like, you could think about this negative 1 here as telling you the arithmetic world. That answer your question, Kyle? Last little thing here is a warning. So let's start with something pretty easy. What are the eigenvalues of this first matrix? And I'll give you a hint. It's a diagonal, it's a triangular matrix, so the eigenvalues are just 2, right? And what are the eigenvalues of this other triangular / diagonal matrix? Still 2, right? So these matrices have the same eigenvalues, but they are not similar. So just to be clear, similar implies same eigenvalues, but same eigenvalues does not imply that they're similar. And then there's also a secondary note here. Notice that row operations usually change eigenvalues. So if you're trying to find eigenvalues, be pretty careful by using row ops. Everywhere else in this class, we've used row operations and row reducing. Like we ref things like it's our favorite thing in the world. We're like, sweet, I can put it in my calculator and hit ref, and we're really happy about it. But be very careful about that in the context of eigenvalues.